For a successful legged robot application in the real world, real-time adaptation to the unseen scenario is needed. These unseen cases can be a sudden change of terrain or of payload, or maybe something on the robot broke and needs to be compensated for fast. All of the videos you'll see here are examples of real-time processing without the use of vision sensors, only a proper set of sensors. And here the robot is traversing down the stairs without really knowing that they exist. Basically, it's trying to stabilize after it discovers the stairs through a fall. And over here, even with the onboard vision, it couldn't ever detect the dip hidden in that bush. And here's an example of the robot trying to stabilize while traversing unstable, loose ground that never behaves quite the same. And all of these clips presented are deployed without any modification or tuning with just one governing controller policy. It was all trained without any real-world acquired samples even. This is the novelty of this paper. The traditional approach has been to get a constrained dataset for a unique set of obstacles to learn a controller and achieve stable locomotion in a single environment. But here instead, the generalization arrives first. The controller algorithm works across multiple environments with no extra effort. So this is a paper about a novel method for stable all-terrain legged locomotion, and it was published in Robotics Science Assistance Journal in 2021. Some quick things to point out about the authors. They'll share a rich background in robotics or related research. They work at University of California at Berkeley, Carnegie Mellon, and the Facebook AI Research Group. A one-slide summary: the Rapid Motor Adaptation, or RMA, has two key parts, a base policy and an adaptation module. Both are responsible for a specific set of resulting behaviors, and the combination of both enables fast adaptation to situational changes. RMA is an algorithm that is trained only in a simulation on various generated terrains. It's really a special case because it requires no need for predefining parameters, such as path planning or pre-generation of limb movement. It was deployed successfully without any fine-tuning whatsoever on the Unitree A1 legged robot and evaluated on a large set of different difficult terrains that you saw. Let's touch on some details of this method. Firstly, they solved the problem in the simulation. They trained a policy which could handle a diverse set of environment variations, and this policy took the current state of the robot and a compressed version of the ground truth environment parameters. There were 42 different ground truth parameters used as input to the policy to learn to walk in all these different settings. They didn't use a generic policy, but instead an adaptive one, which knows what it's dealing with. Through this compressed environment vector called extrinsics, or C sub t, it holds 8 values in total. In simulation, it is going to experience many different environment configurations, and each of these correspond to a different vector of extrinsics. They trained this end-to-end using PPO with 1.2 billion samples. PPO, or Proximal Policy Optimization, is a method for reinforcement learning. It was learned on fractal terrains from a terrain generated within the Unity environment, and this returned the OK-looking gate on the right. But when they deployed this in the real world, there is no ground truth anymore. And the problem is even worse than that. The real-world values of these derived parameters will vary from one terrain to another, so no single choice is correct. Even if it is measured in one place, it will always fail to work in every other place. And the proposed solution here is to estimate these extrinsic parameters online during runtime. The key insight was that the difference between the command to action and the actual movement is a result of this extrinsics vector. And now with this in mind, they learned a new adaptation module to estimate these parameters in real time, given whatever sensor data was there, and then the robot continues to estimate them during runtime. Now the policy is ready for deployment. This adaptation module estimates these unknown extrinsics online, and due to limited onboard compute capacity, it runs asynchronously 10 times per second. That's much slower than the base policy that runs 100 times per second. This asynchronous system is actually critical for seamless real-world deployment. They didn't need any synchronization or calibration while transferring the policy to the robot either. This is an example with a greasy plastic surface. As the robot took to try to cross the surface with the additional difficulty of plastic covering its feet, it successfully crossed it. We can see the robot adapt in real time to the changed substrate and conditions. This here shows the estimated extrinsics over time with 2 extrinsic dimensions out of the 8. The robot slips at around the 3-second mark, and we can see the corresponding change in the estimated extrinsics. This enables then the robot to recover and continue going over the slippery patch. Even after the adaptation, the extrinsics vector does continue to capture the fact that the surface is slippery. What's exciting about RMA is that it doesn't use any carefully tuned control stack, but instead adapts online to show generalization to terrains, which are not seen during training. Lastly, the asynchronous design allows for easy deployment even despite low onboard compute capabilities.